So in this video, we're gonna be looking over homogeneous linear equations, and we're gonna develop the general solutions for these things. And we're gonna be looking over some practice problems and try to knock some out. So if you don't know what a homogeneous linear equation is, pretty much it kind of looks like this, where a right here, this is just a constant. This is the second derivative of some function y. Then we're adding another constant b times the derivative of the function y, but this time it's once, the first derivative, second derivative, and then we have c yx, and this is all equal to 0. So we want to solve for the general solution y of x for these things. And yeah, so pretty much the first approach that we're going to be doing here is, notice how when we take the derivative of y with respect to x, all we're getting is just constants in the front. Every time we take the derivative, we're just getting constants. And there is one function that when you take the derivative of it, it just spits out a constant, and the function y of x stays the same. Now, what is that function? Well, y of x is going to be e to the x, because whenever you take the derivative of e to the x, you just get the same thing back. And we're going to have a constant r. So that way, every time you take the derivative, yeah, it just spits out a constant. And yeah, we're just assuming the solution in this form. So when we apply it to here, we're going to get a times r squared e to the rx. So that's the second derivative of y. Then we have b, our first derivative is just going to be r e to the rx. And then our y of x, that's just y of x. So now we have this. What we could do here is factor out an e to the rx and divide both sides by e to the rx. So we could completely get rid of the e to the rx. So we have bam, bam, bam. And now we're just left with a r squared plus br plus c is equal to 0. And if you want to solve for r, if this looks familiar, we're just going to use the quadratic equation to solve for r. So we have r is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So here is the equation if we want to solve for r. Once we solve for r, we could just plug it in here and then bam. But notice how this is plus or minus. We're getting two solutions from this. So depending, yeah, we're gonna have two solutions, r1 and r2, where let's say r1 is when you add the square root and r2 is where you subtract the square root. This right here is called the auxiliary equation of this differential or this homogeneous linear equation or whatever. And the general solution to these things, which will become useful later on. So we'll be getting two solutions. So we'll be getting y1x is equal to e to the r1x, and then we'll be getting y2x, which is e to the r2x. We'll be getting two solutions to this differential equation. But if we want a general solution for these things, our general solution, y of x, is going to come in the form of c1, which is just a constant, times our first solution. So our first solution is y1x, plus c2, another constant, and times our second solution. And this would be the general solution for this differential equation. This comes in useful when we solve for initial value problems. And yeah, that's pretty much all you need to familiarize yourself with is the auxiliary equation, which is a r squared plus br plus c is equal to 0. We need to write out the auxiliary equation for each of these. This is our general solution for these types of equations. And then here are our are kind of like independent solutions for this equation. And yeah, let's just tackle some problems. So here I put up a equation, and yeah, we're just gonna take the same approach as we did with the general solution. So right away, we're just gonna write the auxiliary equation for this, which would be 2r squared, or let me just start off from the start. So we're assuming the solution is in the form y, I'm just gonna put this as 0. We're assuming the solution is gonna be in the form e to the rx, and we wanna solve for r. So when we plug this in to the differential equation, we're gonna get 2 times r squared e to the rx plus 7. Then the first derivative of this is just r e to the rx minus 4, then that's just e to the rx is equal to 0. Again, we could factor out an e to the rx and completely get rid of it. So bam, bam, bam. And now we're just left with 2r squared plus 7r minus 4 is equal to 0. And this right here is our auxiliary equation associated with this differential equation. So now that we have our auxiliary equation, we're just gonna use the quadratic equation to solve for this. So r is gonna be equal, rb in this case is gonna be 7, but this is gonna be negative 7 out here, plus or minus the square root of 7 squared minus 4, 2, negative 4, then 2a, which is 2, 2. So let's just kind of make this smaller. So 7 times 7 is 49. This right here is going to be 32. This is going to be 49 plus 32. So we have r is equal to negative 7. So 49 plus 32, that's going to be 81. So I'm going to get rid of this. Going to get 81 on the inside, but this is just going to be 9. So 9 over 4. So our first solution here, we're going to have r1. Let's just put it when it's plus, so negative 7 plus 9 over 4. And that's going to be equal to 1/2. So here we have r1. And now let's do it for the minus case. So we have r2 is equal to negative 7 minus 9 over 4. We're going to get negative 16 on the top, and r2 is just going to be negative 4. So now we have our r1 and our r2 values. So now that we have our r1 and r2 values, we can just plug it into our assumption. So our first solution for this differential equation is going to be e to the 1/2 x. So bam, that's one solution. And y2, we're going to be using r2 for this, and that's negative 4. So we have e to the negative 4x. So these are our two solutions for this differential equation. But if we want the general solution for this, we're going to be using the general solution formula. So yx is going to be c1. This is our constant, but because this isn't an initial value problem, we're not going to be solving for this constant. We're just going to leave it as it is. This is just the general solution for it. Then we're going to put in our y1, which is e to the 1/2 x, plus c2, then e to the negative 4x. So right here would be our general solution for this differential equation here. And yeah, now we can move on to a differential equation, but let's apply some initial value points. Okay, so here I have another differential equation, but right here we have some initial points that we also need to apply to this equation. So let's just do the same approach as we did with the other problems. So I'm just gonna skip writing that we're assuming that y is gonna be e to the rx. Our auxiliary equation for this is gonna be r squared plus r, which is equal to 0. We can just factor it out. We don't need to use the quadratic equation for this. We just factor out in r. So r times r plus 1 is equal to 0. So right there, we already have both of our values for r. So r1 can be 0, and r2 can be -1. So right there, we already have our values for r. So with our values, r1 and r2, we could have our solutions. So y1 is going to be e. So the form was e to the rx. If r is 0, then e is going to be to the power of 0. So this is just going to be 1. And then our y2, when we plug in -1, we're going to get e to the negative x. So here is both of our solutions for this differential equation. And our general solution is going to be yx is equal to c1. And our y1 is just 1, so I'm just going to leave it as c1 plus c2. Then we have e to the negative x. Now, this is where our initial points come in play, because these points are going to allow us to solve for our constants. So because this is y of x, and we have a y prime up here, let's just take the derivative of y of x. So our y prime in this case is going to be negative c2 e to the negative x. The derivative of a constant is just 0. So now we have these solutions. Applying these initial points, we could just straight up just apply them. So our y, when we use this one for this equation on the top right here, we're going to have x equal to 0. And this y of x is going to be 2. So we have 2 is equal to c1 plus, when x is 0 right here, we're going to have c2. So we have this equation. On the bottom here, we have y prime of x, this part, is going to be equal to 1. And our x is going to be 0. So we're going to have 1 is equal to negative c2. And e to the negative x, that's just going to be e to the power of 0, which is just 1. So we can just leave it like that. And right here, we pretty much have a set of equations that we have to solve. And when we solve it, we'll be able to solve for our constants. So for this bottom one, it's quite clear that c2 is just equal to -1. And if c2 is -1, then for this top one, we have 2 is equal to c1 minus 1. And then that leads to c1 is equal to 3. So right there we have our constants, and we could just apply these constants to our general solution. So our general solution was y to the x is equal to c1, which c1 is our 3. And then y1, we're just going to leave it like that. So this is our first part, plus our c2, which is -1. So I'm just going to replace that plus with a minus. Then our y2, which is e to the negative x. And here, this would be our solution for this initial value problem. And yeah, that's pretty much about it for this problem. So here I have another differential equation. However, this one's a bit slightly different. You'll see in a bit why, but let's just approach this. So first, let's write out the auxiliary equation for this. So I'm just going to skip the assuming y of x is equal to e to the rx. So we're going to get 4r squared minus 4r plus 1 is equal to 0. And if we want to solve for the both values of r, we're just going to use the quadratic equation. So negative b, our b in this case is -4, so on the outside we just have a 4, plus or minus, then negative b squared, which this is This right here would be a negative 4 squared minus 4a 4 then c1 all over 2a. Okay, notice how on the inside here, negative 4 squared is 16, minus 4 times 4, that's also 16. So this square root just turns into a 0, and then r becomes a double root. So r really takes on the values 1/2 and 1/2. R1 and R2 in this case are the same. So technically we would have both of these as solutions for our differential equations. Even though they're the same thing, they're technically both, I guess, separate for what we know right now, they're both the same. Okay. So these are the pair of solutions that we would have for this differential equation. But even though they're the same, I'm just gonna put it like this for what we'll see in a bit right here. So let's say instead of this differential equation, like just by itself, let's say we had an initial point. Let's just say we had initial point values. So this is equal to P0, then y of T1 is equal to P of 1. So now we have these initial conditions. And let's say we try using this formula. So our general solution for this is just going to be C1 times our first solution, so e to the 1/2 x, plus C2, then e to the 1/2 x again. What we can do here is factor out an e to the 1/2 x. So we'll get C1 plus C2 times e to the 1/2 x. And this right here, C1 and C2, that's just another constant. So I'm just going to label it as C e to the 1/2 x. And it turns out that if our general solution is in the form like this, we're not going to be able to solve this initial value problem. So really there's like a hidden solution to this. And that hidden solution, instead of e to the 1/2 x or them both being the same, our hidden solution in this case, we're just going to multiply this by an x term. And now this works. And the reason why this works is because this thing called linear independency, where if y1 is equal to a constant multiple of y2, the normal way that we were doing it is not gonna work. So if this were to ever happen, just multiply your second solution by just x. Really, if r becomes a double root, just do this approach where whatever solution you get, whatever is the first solution that you get, just multiply it by an x term, and that's going to be your second solution. So really, our general solution for this differential equation, y of x, is going to be c1, then e to the 1/2 x, plus c2, then we're going to have this instead. So x e to the 1/2 x. So this right here is going to be our solution for this differential equation. If you want to check, just go ahead and plug in this into that, and you'll quickly see how this turns out to be a solution. So here we have a slightly longer differential equation, and we're just going to do the same approach as we did with the others and apply it to this. So again, assuming the solution in the form e to the rx, when we apply it here, our auxiliary equation is going to look something like this. So we have r cubed minus 6r squared minus r plus 6 is equal to 0. Now we can't just apply the quadratic formula here. So here is really where we need to do some algebra to solve for r. So what we could do here is get these two 6's together. So I'm just going to go ahead and write it negative 6r squared plus 6. Then get these two terms together. So plus r cubed minus r is equal to 0. On this left hand side, we can factor out a 6. So we get 6 is going to be equal to negative r squared plus 1. And over here, we can factor out an r. So plus r, then we get r squared minus 1 is equal to 0. And actually on this one, I'm just gonna factor out a negative 1. So that way this turns positive, this turns negative, and we have a negative 6 on the outside. So here, we could just write this as, well, you could just write it like this. So now we have r squared minus 1. So that's our first part. Then we have r, this minus 6 is equal to 0. On this term right here, we could expand it a bit more and leave it as r plus 1, r minus 1, then we have the r minus 6. And here, we have the roots for this differential equation. So we have r1 is equal to negative 1, r2 is equal to 1, then we have r3 is equal to 6. So here, for this differential equation, we have 3 roots instead of our usual 2. Now, when we have 3 roots, we're gonna have to expand our general solution formula a bit more. So now, for our general solution, actually, first off, let's just write the solutions for this differential equation. With r1 equal to negative 1, then we have y1x, our first solution, is gonna be e to the negative x. Then y2x is gonna be e to the x for this one. Then y3 of x, this is gonna be e to the 6x. So these are the 3 solutions that solve this differential equation. But for our general solution, we're gonna expand it. So y to the x, instead of dealing with two constants, we're gonna have 3 constants this time. So we have c1 y1 plus c2 y2 plus c3 y3. So this is what our general solution is now gonna look like. When we just plug in everything, we get y of x is equal to c1, or y1 is e to the negative x, plus c2, or y2 is just e to the x, plus c3, and our y3 is e to the 6x. And this right here would be our general solution for this differential equation. And I want to go over one more thing before closing off this video. So let's say now you had an nth order differential equation. So it would be in the same form, but now you just have a bunch of terms, specifically n amount of terms. And let's say you were given an initial value problem. You don't really have to be given an initial value problem, but let's say you were. You would have a bunch of initial points that you had to satisfy. More specifically, you would have n amount of points to satisfy. So if you want to solve for the general solutions of these things, the general solution that we would get, so y of x would be c1 y1 plus c2 y2 plus c3 y3, and this would go on all the way to the nth solution. So you're gonna have n solutions. When you do the same procedure that we did, so we assumed e to the rx was a solution, and you did this, you're gonna solve for n amount of roots, and thus you're gonna have an n amount of solutions, and this would be the general solution for this differential equation. So if you were ever given a more complex equation of higher order, say 4, 5, 6, this right here is going to be the general solution for that differential equation. And yeah, that's really all there is to this. And yeah, see you guys later.